And so, yeah, well, first of all, I think this is a, well, very interesting seminar series that Thomas and his colleagues have put together. And thank you for that. And it's a pleasure for me to talk in this series. I mean, I'm not an expert on climate change. And as Thomas said, I started as a theoretical physicist. I did theoretical condensed matter physics. And after doing a master's diploma in Germany, I wanted to do something, well, still theoretical, but with an applied background. And at that time, in the mid-90s, fuel cells were a big thing. And they were becoming very popular. And so I started researching that area. Actually, there's no, well, no person who is a trained expert in electrochemistry. Everyone starts out with a different background, either in chemistry or in physics or chemical engineering, some in mechanical engineering as well as mathematics. And so all coming with a different background, bringing different tools and expertise to that field, which makes it a very diverse and interesting field, which has influences from condensed matter physics as well as well, chemistry and engineering disciplines. And so, the way I understand the problem of climate change is there are two parts of it. One is understanding the relationship between the climate and the chemistry of atmosphere, biological matter, and oceans. And the second aspect is providing tools to be able to predict the impact on climate of well, different energy infrastructures involving sources of energies, evaluation of energy conversion technologies, storage technologies, efficiency of energy use, and so on. All of these aspects together. Either of these fields are quite complex, I would say, involving many processes, many materials, many components, degrees of freedom. And so my focus is more on these aspects, and specifically on the electrochemical techniques. And I will talk a little bit about that. That as well is a complex field which has evolved. Many different technologies are being developed. And it ranges from studies of fundamental phenomena to very applied research, technology development together, and it's done together with companies who try to develop electrochemical devices. And so I can only give you like a little bit of an overview of that field. And as I understand, this is an informal forum, so if you feel or if you want any clarification on anything, just feel free to ask at any time. And so, well, okay, so we're talking about energy, and usually in science, physics, chemistry, teaching thermodynamics to undergraduate students, what is considered to be difficult is the concept of entropy. But what I find even more challenging is understanding the concept of energy. If you had to come up with a definition of what is energy, I think everyone here would struggle a little bit. And well, what we can consider it as, I mean, so physicists usually take a simplistic view of things first, and then they make things more complicated. So first of all, it's a physical property that can be assigned to objects, to systems, and it's like add a number or volume. And for a practical definition, this is how actually the term has developed over the last 200 years. During the evolution of thermodynamics, it can be defined as the ability of a system to perform work. So it is an intrinsic ability of a thermodynamic system. And it comes in very different forms. We can define kinetic energy, potential energy, thermochemical, nuclear energies. Mass is an equivalent form of energy, so that we can convert mass into energy. And well, if you want to use that concept in any practical work, we need an instruction to measure it. And what can actually be measured is not the total amount of energy, but energy changes can be measured during processes that are conducted under controlled conditions. So there are these instructions how to measure energy. And well, one question, well, I think in part it was it motivated me to come to this field. Was in my undergraduate studies, I did a course on a similar topic which was related to global energy challenge, climate and so on. The professor teaching it was a theoretical physicist, also he had a very straight and simplistic view of things. And what he tried to hammer into our brains was that there cannot be an energy crisis. There can only be an entropy crisis. So when we want to discuss about it, we should never phrase it as there's an energy crisis or an energy challenge, because there cannot be a challenge with something that is conserved. And that energy is conserved is something that we must all agree on. And it's nothing. It is something that cannot be proven. We just have to accept it. And so. Well, energy, then if you accept that concept, so there's a certain amount of energy of the universe, and we cannot fudge around with it, that total amount is fixed. That's given. But, well, accepting that, one can build a formalism, and that's the formalism of thermodynamics. And in my view, this is the most powerful formal machinery that science has to offer, thermodynamics. And it provides a huge set of fundamental laws, set of instructions of how to calculate things, how to relate things, that govern the distribution and transformation of energy. And so this is, well, these statements here are not meant to be taken personal by anyone here. Also, they are not advert messages for any Italian people in the audience. So, well, I mean, so people not having their primary education in science, physics, or chemistry usually well, have a certain respect when it comes to thermodynamics, understanding the laws of thermodynamics. So this is an intuitive formulation of the laws of thermodynamics. And first one is, you cannot get something for nothing because matter and energy are conserved, always. So that's the first law of thermodynamics. The second law of thermodynamics is you cannot break even. So, well, we cannot start from an initial state, go to a final state, and return then to the initial state. This is something that is impossible. Nature does not allow that. And this is the second law of thermodynamics, which states that the entropy of the universe must always increase. And the third one is also quite essential. We cannot get out of this game. The only possibility, hypothetically, would be to conduct processes at zero temperature, which is impossible. It's forbidden by the third law of thermodynamics. And so these are formulations of these laws taken by C.P. Snow, an English physicist and novelist. I think he was living up to 1980, so the 20th century. And so, well, in thermodynamics, there are two main approaches. One is the phenomenological one, and this is how thermodynamics was developed. First, there was a steam engine, and then thermodynamics was built around it to understand how that engine works, and develop it further and bring it to applications and so on, and we know what all came out of that. And the second approach is to develop that formal machinery. And thermodynamics has an even more evil sister, which is statistical mechanics, and they together will allow to establish a huge number of relationships between states of matter under various conditions, environmental conditions that can be controlled, like temperature, pressure. The composition of system can be varied, and the laws of thermodynamics, this formal machinery, relate all these properties to each other. And well, these are, again, these empirical laws. And for, well, as I said, so energy is a term that is difficult to define. We just have to accept this is a property intrinsic to matter, intrinsic to any physical system, and the total amount of energy in the universe is conserved. Entropy is something actually we can get to kind of an intuitive understanding. If you assume that we have a number of boxes, we have a number of objects to distribute. So in thermodynamic equilibrium, the distribution of, let's say, we have 100 balls to distribute over, let's say, 10 bins. In thermodynamic equilibrium, the distribution will always be uniform, at least on average. So if you take a time average, so we take snapshots of that system at random times, and then take the average over these distributions that we can determine. The distribution of these objects, which are not anyhow labeled, over the available bins will always be uniform. Or maybe even a better example would be after an event in a big stadium like EC Place, 50,000 people have, let's say, 10 exits over which they can leave. So if they would all line up in front of one exit to leave, that would correspond to a very low entropy state. And so nature always does things in a way that all these people would try to distribute more or less uniformly to all the different available exits. And so this is also a fundamental trend implanted into nature. So all processes in nature, if they proceed spontaneously, will obey this, or will follow this trend. And so, as I said, it's a very powerful machinery which gives us a set of rules and it allows us to predict a lot of things, for instance, the spontaneous direction of reactions, chemical reactions or processes. We can determine the equilibrium constants of reactions that have never been run. And we can determine how equilibrium constants depend on temperature. And we can precisely specify the state of matter or of any physical system. And so this is, well, these are empirical laws. So the laws of thermodynamics are empirical laws. There are no fundamental principles on the basis of which they could be derived. We just have to accept them. And, well, the good reason to accept them is that they have never been violated. So there is no observation that has ever been made which is at odds with these laws of thermodynamics. These are just a few statements by famous scientists who in principle formulate the same thing. So that classical thermodynamics is a rock, and we should not try to shake its foundations because they are very solid. And so now, well, so there are a few energy estimates, or estimates related to the global energy. So what is the basic energy demand? Well, I mean, so these are very plain and simple estimates. I think they are in a certain way useful, but of course, well, in reality, things are much more complicated than what I will present here. So there's basic energy demand. Then you can compare that with the actual energy consumption. You can calculate something like an efficiency. And so I took, just for a rough estimate, basic energy demand of 2,500 kilocalories per person as an average. I can calculate the total energy input needed per day, and that is this number, huge number. Another huge number is the global energy consumption, so these are known data that one can retrieve from the internet or from more credible information, source of information, and so one gets another large number. Then we can calculate the relation of these two numbers, and it gives us an average efficiency of about 5%. So, and well, another interesting number is to compare these two with is the total amount of energy that is hitting the Earth coming from the sun. This is basically our only interaction, only significant interaction with the rest of the universe. It's the energy that arrives on the Earth from the sun. And that is this number, a large number too, but many orders of magnitude larger, as you can see here. And actually it's about 10,000 times the global energy consumption. Now the way that our biosphere uses this energy is mainly by photosynthesis. Photosynthesis is a relatively inefficient process, about, well, significantly less than 1% efficient. And actually, photosynthesis is a mechanism by which the Earth can be kept in check. So because the energy that comes from the sun is energy that has a low entropy associated with it. And in order to keep the energy balance, so entropy, a certain amount of energy arriving at the Earth with a low entropy. In order to keep the energy balance in check, the Earth is radiating into the universe, and that radiation is high entropy energy. And so by having this energy exchange from the sun to the Earth, conversion of low entropy energy into high entropy energy, the entropy balance of the Earth can be kept in check. And so that I would call truly sustainable conditions. So it's related to the entropy. It must be related to the entropy. And photosynthesis is mainly the process by which this happens. But as you see here, this is something that you should keep in mind. Photosynthesis is highly inefficient. It's not a very efficient process. Less than 1% efficient. But this is sufficient to keep that entropy balance in check. And so what we currently use, about 86% for our human activities is energy from fossil fuels, and so that we can refer to as stored sun. And another interesting aspect here is that all the economic action, all economic models and so on, are still, at least in my perception, based or predicated upon unlimited access to fossil fuels. And of course we know that this is not the case. This is an unrealistic assumption, and something that must be, an assumption that must be relaxed. So now this is the three-course recipe for the disaster. So it is purported that, over the next 40 years, towards the end of this century, the energy input required for our actions will double, at least double, and by the end of the century it is going to triple. If extrapolating the current scenarios of energy use. At the same time, it is also well known and documented and now widely accepted, that we are actually already feeling the finiteness of the resources that we are relying on. So we are living on a finite planet. The resources in oil, gas, coal, and so natural gas, coal are limited, and most likely in oil extraction we are already beyond the peak. So this was predicted to occur sometime between 2000 and 2010. And one interesting aspect here is, so this is oil extraction over a time span of about 180 years. So in about 100 years it was ramping up, and in about 100 years it will go down significantly. And so this is a pretty daunting scenario, considering how much of our activities actually depend on the input of this resource. And also another interesting aspect here is, seeing this as a physical chemist, chemical physicist, I'm tempted to integrate this curve up. Then you could take like an average price of oil per liter, and you could calculate how much wealth actually is contained under this curve. And there are certain countries, of course, which are suppliers of this commodity, or this resource, which are exporting it. And for them, this will be accumulated wealth, which must somewhere be in their economies. There are other countries which have to import this in order to produce infrastructure, knowledge, commodities, and so on. And for them, it is money that they must have spent at some point. Fortunately, this resource was extremely cheap over the recent 100 years. And so probably in the economic balances, it's not a very significant factor, but it must have generated a tremendous amount of wealth. What this shows here is a Human Development Index. So this is a quantifier of well-being of societies distinguished by countries. So it represents like again, infrastructure, access to education, well, access to goods, and so on. So it's a component index published well, every couple of years, I believe, by the United Nations. And here it is plotted as a function of the energy use per person and per year. And so one can see here, well, first of all, there's a wide range of variation in terms of energy use. Of course, the so-called developed countries are on this side, the developing countries are on this side, third world countries. And the trend looks like a more or less monotonic trend. So, well, with increasing energy input, the human development index is increasing. On the other hand, there's a need well, at about this range here, and above that value, the dependence becomes very weak. And below this threshold, there's a very strong dependence. And one can convert this into this energy efficiency that I used before, on, well, one or two slides before, and see, well, the energy efficiency of the countries that are here is extremely poor. And so if energy efficiency actually were considered to be, well, as an indicator of the development of a society, then certain societies would not look very good from this perspective. And so this is the global average here, and about 40% of this human development index corresponds to, let's say, the limit of starvation. So this is the minimum energy input needed. And for those of you who were here last week when Peter Berg discussed this, energy slaves, so you can directly convert this energy efficiency into this number of energy slaves. It's an inverse proportionality. And so now,